So in the class graph theory video, we saw some properties of normal trees in a graph. We saw that if we can find a graph and a normal tree in it, then the graph is in some sense an expanded version of the tree itself. So looking at the tree, we can say some things about the graph. Now in this next result, proposition 156, we are saying that if we are given a connected graph, then with any specified vertex in that graph as the root, we can find a normal tree in the graph, and that too, that tree will be a spanning tree. So we won't miss any vertex of the graph. All the vertices of the graph are also going to be vertices of the tree. So let us now see how we can prove. We can prove means we are not going to prove this on our own, of course. We are going to, rather I should have said how Diestel has proved it. In all our videos, not just in graph theory but the other things, so far we have just simply had the modest aim of trying to make sense of what the authors have done. We haven't done anything much on our own, aside from maybe solving some exercise problems. When we manage to complete a significant portion of the things that we are going through now, then we will make some general remarks on these things. That is, we are going to put forth our own views on these things, what we think these things are. That will be a little something new. Other than that, everything is just already there. We are trying to understand the things. So the proof that appears in the text is this. Let G be a connected graph and R belonging to G be a specified vertex. So this vertex is going to be the root of the spanning tree that we are saying, spanning normal tree that we are saying exists in G. And this R belongs to G simply means your more accurate notation that R is a vertex in G, which we write like this more simply by abuse of notation. Let T be a maximal normal tree in G with R as its root. Okay. How exactly? How do we know that such a maximal normal tree with R as its root will exist in G? This is our G, which is some connected graph, and R is some vertex in it. Now what is normality? If you have a rooted tree T in a graph G, then T is said to be normal if the ends of a T path in G are comparable in the tree order in T with respect to that root. And T path by definition is a path only whose ends only are parts of T. Everything else in the path is outside of T. For this particular tree, this single root, this single vertex is first of all a tree in G. Why? Because it's non-empty, it is connected, and it is acyclic. So it's a tree. Now this condition for normality is satisfied by this tree vacuously. That is because there is no T path. any such path-like structure you can think of in this situation that starts here and also ends here is not a path actually. So that is why vacuously this is a normal tree in G. Now, so that tells us that G has a normal tree with R as the root. I mean, you can think of this as the root. Then you can start growing this tree from this root. You add one more vertex, you introduce one more vertex that is adjacent to this one. See whether normality is satisfied or not. If not, I'm just simply saying, okay, without thinking anything of normality or without actually applying the definition of normality, I'm just simply saying that normality is a property. So what you do is that you keep introducing new vertices one by one and checking whether normality is retained or not. Because we are in a finite graph, only in chapter 8 we are going to consider infinite graphs. All our other graphs are in general finite. So this process ultimately will give you a maximal normal tree T. This, however, feels a little non-rigorous. For that, what you do for a rigorous argument to claim that such a T exists, you can take the help of Zorn's lemma. You consider S to be the set of normal trees in G with R as root. This set is non-empty because this tree with the sole vertex R is an element in this set. So it's a non-empty set, and you can partially order it with the subgraph relation. One graph being a subgraph of another graph. That relation orders this set partially, because that relation in general is a partial order. It is reflexive. Any graph is a subgraph of itself. It is transitive. If A is a subgraph of B and B is a subgraph of C, then A is a subgraph of C. These things we saw in the very first section itself. And it is antisymmetric. If A is a subgraph of B and B is a subgraph of A, then A and B are identical. So this is a partial order in general. So in particular on this set also it's a partial order. So we now have got a partially ordered non-empty set. In this, if you consider a chain, which is by definition a totally ordered subset of S, then that chain will have an upper bound. That is because since we are had we been in an infinite graph, the situation would have been somewhat more complicated, but we are in a finite graph, so the number of possible trees that are subgraphs of G is finite. That means the number of possible trees with R as root and which are normal in G are also finite. In particular, this set is finite. So being a subset of S, U is finite. So there are only finitely many elements in U. And because this is a chain, any two elements are comparable. You take any two trees from here, one of them will be a subgraph of the other. That is why, and that is why in fact this is also called a chain. So the elements in T will look like this. you can order them in this way. There will be a maximum element, and that maximum element clearly is an element in S, which is an upper bound of U, because all the elements in U are less than or equal to that maximal element. So by Zorn's lemma, that maximum element. So by Zorn's lemma, the set S itself has a maximal element, and that one such maximal element is T. Okay. We now show that this T is actually a spanning tree. That is, the set of vertices of T is equal to the set of vertices of G. That is, T has all the vertices of G. In chapter 8 of Terence Tau's analysis 1, we haven't got to that stage yet. We will come across these things: ordered sets, Zorn's lemma, its equivalence with the axiom of choice, those things, well ordering principle. Okay, so now our aim is to show that these two things are equal. Suppose not. And let C be a component of G minus T. Suppose not means we are supposing that T is a proper subgraph of G, that is, there are vertices in G which are not in T. So that means if we remove T from G, there still will be something in G, and that removal may create many such islands of connectivity or islands of connectedness. Among those islands, C is one. So we can draw a little figure here. Okay, so C is one such connected component of G minus T. Since in the very next line we have this, since T is normal, N of C is a chain in T. Now what is this? And what is N of C? We first need to recall that. N of C is the set of those vertices of C, well, not of C, okay, in the beginning itself I said it incorrectly. N of C is the set of neighbors of the vertices of C that are not in C. That means, say you have a vertex in C, it has some neighbors like this. Among these neighbors, these three are in C, but the things that are outside, they belong to N of C. Those neighbors of this vertex that are not parts of C, okay, all such neighbors of all such vertices which themselves do not belong to C form N of C, this set, okay. Now we are saying that because T is normal, this n of C is a chain in T. Now to justify that, there are some things we need to say. So let us write these things within brackets. I need ink already. These extra things are not there in the text. We are supposed to figure these things out on our own, which we are doing, fortunately. It is like that thing, this existence of this maximal normal tree T. For the author, these things are obvious. Hopefully one day we will achieve his, well, not his level, not that I am saying, but at least we will be, these things at least will also be obvious to us if we spend enough time here. For now, however, we need to justify them painstakingly. Let T1 and T2. So let us first, even before writing these things, let's first see what this line means. N of C is a chain in T means, first of all, you need to somehow show that N of C is a subset of T. Okay, and then it is a chain in T means T already has an order, I mean, or rather, more specifically, the vertex set of T has the tree order in it. Okay, with respect to that root R. With respect to that tree order, this is the chain, this is a totally ordered subset. So let us see how we can do that. Let T1 and T2 be two elements in N of C. Then T1 and T2 do not belong to C. Yes, by the definition of N of C, they are not in C. Since C is I am keeping the statement. There is no need to keep the statement. We need space anyway. We have already seen what the statement asks us to do. Since C is a component of G minus T, T1 and T2 must be in T. Why though? You see, T1 belongs to N of C means what? First of all, T1 is not in C, and the second thing is it has a neighbor in C, because we are considering neighbors of elements in C which are not in C. Now, being not in C means it is either in T or in one of these components, if they exist. If it belongs to some component, say it belongs to here, then there is a problem. The problem is that removal of T creates these components, and removal of t does not remove this edge, no, because this edge has both its ends not in t. This end of already is not in t because it belongs to C, and C is a subgraph of G minus t, and the other end according to our supposition does not belong to t, and that is why it belongs to some other component. But then if even after removing t this edge is still there, then how are these two things different components? They will be form a single component. So that is the problem, and that is why this T1 actually must belong to T. There is no other choice. Like that, T2 also belongs to T. Okay. So T1 and T2 both must be in T. Let U be a neighbor of T1 in C and phi be a neighbor of T2 in C, and such neighbors exist because these two things are coming from N of C. So note that we have already shown in these lines that N of C is a subset of T. So now we need to make sure that N of C is a chain. That means any two elements in N of C are comparable with respect to the tree order in T, with respect to that root which is here somewhere. Okay. So by the definition of N of C, for each such element in N of C, that is a neighbor of something in C. So maybe multiple, it may be the neighbor of multiple elements in C. At least one will be there. So for T1 we have U, and for T2 we have V. And we are not saying anything like this U and V are distinct. They may be the same thing also. Okay. Since C is connected, there is a UV path in C. After removal of T, we have this connected component C. So being two vertices U and V of C, there is a UV path in C. In case this U and V are they coincide, that single vertex is a UV path. Okay. The point here is that this UV path has nothing to do with T because it is in C, and also because it is in C, it has nothing to do with the other possible components that may exist. It is solely lying inside C, and that's just it. This UV path along with the edges T1U and T2V give us a T1 T2 path, that is a T path this one, and this path is in fact more simple actually if u and v coincide. In that case we have just this, but that whatever the case is a t path. Its ends t1 and t2 are in t, but these other things, this portion, the p path or I mean the uv path, of course is not in t at all, and these two extra edges, they are also not in t, because these two ends do not belong to t. So that is why this t1 t2 path is a t path since only its ends belong to t. Since t is normal, t1 and t2 are comparable in the tree order of t. That means what? That the ends, I mean this any two vertices in N of C are comparable in T. So in T, in that partially ordered set T, or rather its vertex set B of T, N of C is a chain, a totally ordered subset. Let X be the greatest element of N of C. Okay, so now we don't need these things. We have a vertex X in N of C that is the greatest element of N of C. Now what about this greatest element? You see, already N of C is a subset of T and it is totally ordered. So being a subset of a partially ordered set, N of C is also partially ordered, and since there are only finitely many vertices, so there will be maximal elements. Again using Zorn's lemma, like how we have made sense of the existence of T itself, a maximal normal tree in G with R as the root. This is not OR, okay, this is the vertex and this is R. But because N of C is a totally ordered set, a chain, so those maximal elements will be comparable among themselves. So using that, it follows that there is exactly one maximum element, and that maximum element is the greatest element X. So such an element will always exist. And let Y be its neighbor in C. But fine, this is the greatest element in N of C, but being a vertex in N of C, it must be a neighbor of something in C. Let that something be Y. It may be a neighbor of many such somethings, but at least one such vertex is there. So let that vertex be Y, excuse me. now what we are going to do, we are going to extend the tree T by introducing this extra vertex y and this edge. Because we are considering only one vertex and one edge, the supergraph, resulting supergraph will be a tree. You cannot introduce a new edge among the existing vertices of a tree. That will create cycle. Okay, but because we are introducing a new edge that exists between a vertex in T and a new vertex, so no cycle is being created by this process. So that's what we write. Let T prime be the tree obtained by joining x and y. Or joining y to x, same thing. The tree order of T prime extends that of T. In fact, what is the tree order? According to that tree order, x is already a maximal element in T. Okay. That is because there is no higher element than x. Here in T we are not considering y for the moment. So after that, extending the tree order means y is a new vertex that is greater than x in that new extended tree order. That's what we are saying. So the order of T prime extends that of T, extends the order of T. We shall derive a contradiction by showing that T prime is normal in G, because then the maximality of T will be violated. We have a proper supergraph of T that if we now manage to show is normal in G, then maximality of T is violated. So for that, let P be a T prime path in G, that is a path in G only whose ends belong to T prime, this extended tree, this tree and this edge along with its other end. If the ends of this, we have given it a name, if the ends of P belong to actually T, if it is like this, then P is a T path and normality of T in G implies that the ends of P are comparable in T, that is comparable in the tree order in T. So the ends of P are comparable in T prime because the tree order in T prime is just an extension of the tree order in T. So I assume that the ends of P are not both in T, but both cannot be outside of T because outside there is only one vertex, and the ends of the path, this T prime path, must be distinct because it's a path. So one of them must be Y and the other end must be here in T somewhere, and the actual language is this, or let me just write it in my own words. Thus one end is Y and the other end, which we can call Z, belongs to T. Now note that this new path now, it looks like this. One end is Y and the other end is Z, but because it is a T prime path, so this path starting at Y and coming to Z, it enters T prime at Z only. Okay, and that is why this path lies entirely outside T prime except for its ends. So that means what? That means that this Z will be a neighbor of something in this path now. The vertex just before Z. That vertex does not belong to T because that is the nature of the path. That is why it is a T prime path. That vertex does not belong to does not belong to T, and this vertex Y also does not belong to T. So that part, where will that vertex belong? Because it does not belong to T, it will belong to one of these components. However, it cannot belong to a component different from C. Why? That is because since this thing is a path and it lies entirely outside T, so this path exists even after removal of T, and the path starts at a vertex in this component C. So if the path ends at some other component, then some other component will actually not be an other component. It will be the same component as C. So that's why this vertex is forced to be inside C itself, and we have an edge like this. And what does that tell us? it tells us that this Z is not just in T but in N of C. So we write like this things. P is a T prime path. Z belongs to N of C. Then Z is less than or equal to X. Okay, Z is less than or equal to X because X, according to our choice, is the greatest element in N of C. So Z may be equal to X or it is strictly less than X. It's thus enough to show that y is greater than x in the tree order of T prime. That is, x belongs to this path joining the root r and y, and that is evident. This is evident because we have created the tree T prime by just joining this extra vertex y to x with an edge. So automatically the path in T prime, in this larger tree that joins y to this root, must pass through x. There is no other there is no other path. So that is why x in the extended order of T to T prime, in that order x lies in that unique path joining y and r. So by the definition of the tree order in T prime, y is strictly greater than r. So y is greater than r and z is less than or equal to x. That tells us what? Using the fact that this partial order is transitive, so z is now less than x. That means this ends, y and z now in this case also are comparable in the tree order in T prime. So that is why T prime is normal in G, and this is a contradiction because T prime is a proper supergraph of T which was chosen to be the a maximal normal tree in G. So that is why our supposition is wrong. What was our supposition? That the vertex set of T is not equal to the vertex set of G. That is, it's a proper subset of the vertex set of G. This is wrong, and that's why that maximal spanning tree T in G must actually be the maximal normal tree T in G must actually be a spanning tree, and so this completes the proof, and it completes this section also. In the next section we will see bipartite and multipartite graphs, that is graphs in which the vertex set can be divided into some clumps so that any edge in the graph has its ends in different clumps. We don't have a thing like this. Okay, this has become a smiley face. We don't have a thing like this. If there are two such clumps, then all the edges look like this, and the graph is called two-partite or bipartite. We will see that a graph is bipartite if and only if it has no odd cycles, if I am remembering the result correctly. So with that, I end this video. If you want to say something on these things, you can use the comment section below, or you can mail me here at this address. So today is Tuesday, na? Wednesday, Thursday. Next Friday we again have group theory from Herstein's topics in algebra. So that will be all. So see you next Friday. Signing off from the mathematical room. This is me, Lucifer. Have a nice night.